Good evening. We have this video on combined and beam type footing. So before this, we are with axial load and uniaxial moment. Now, when we have load is larger or greater on column, in that case, we will go for combined slab and footing because in that case, depth required for slab is more and to provide economical footing, we are going for this. Means the change in this we have slab type footing. In that one we have slab throughout. So we have same in this way, but this slab is designed for transfer moment, means moment from this side, and then we have one column over here, we have another column over here, and the column having maximum depth, we are going to provide width of beam equal to it. And so likewise, we are going to provide beam. So this beam is to resist loading along the length, and the slab is responsible for loading along the width. So slab is designed for transverse load and beam will design for longitudinal load. So now we have this problem, two interior column, A and B carry 750 kilonewton and 105 kilonewton loads respectively. Column A is 350 by 350 and column B is 400 by 400. So my width of beam will be 400. The center to center distance between column is 4.5 meter. The SBC of soil is 150 kilonewton per meter. We have to use M20 and then Fe500. So design a combined slab beam type footing by limit state method. So we have first given data. So we have given PUA 1.5 into 750, 1125, and this is 1.5 into 1050, so equal to 1575. So 1050 into 1.5. So we have 1575 kilonewton. In class already we have seen, but I forgot to correct it. So we have 350 by 350 mm column A, column B we have 400 by 400 mm. SBC is given 150, so 1.5 into 150. So we have this as 225 kilonewton per meter square. M25, Fe500. RU max we have 0.36 FCK KU max, 1 minus 0.42 KU max. So for Fe500, we have 0.46. And from this, I will get RU max 3.34 kilonewton per mm, sorry, Newton per mm square. So here I have made correction, but in first step I forgot it. Then we have step same area required. So we have total load on footing upon ultimate SBC. So we have this will be column load of A. This is ultimate column load of A. This is ultimate column load of B. And 1.1. So we have considered self weight of footing equal to 10%. Equal to 10% of column load. 10% of column load. And therefore it is 1.1. So 2970 upon 225. And we have this value 13.2 meters square. So now you have to provide size of footing. Width you have to assume, now we have already seen, we have to provide beyond column minimum 0.5, 0.5. So if we will calculate it, so we have column depth 0.4. Beyond this, we have 0.5 plus 0.5, and we will get this value 1.4. So beyond 1.4, you can provide any value. So I have taken it as 2 meters. Then we have LF. So area required equal to width of footing 13.2 divided by 2, and we have this value 6.6 meter. So now we have length 6.6 meter and we have width 2 meter. So we have provide LF equal to 6.6 meter and BF that is equal to 2 meter. So now we have this is area provided if we will go. So we have 13.2 meter and that is equal to area required. You can go higher side but need not require in this case. Then for uniform pressure distribution, CG of column load and CG of footing should coincide. So we have this is footing. This dimension that is width of footing we have 2 meter. So we have provided this as 2 meters. And length we have provided that is 6.6 meter. Now load on distance between two columns 4.5 meter. Load on column A 1125 kilonewton, on B 1575 kilonewton. So now X bar, so we are taking moment about column A. So moment about column A. And then we have summation of P into X bar, and that is equal to P1X1 plus P2X2. And same we have kept over here. This is summation P into X bar equal to 1125 into 0 because moment we are taking that is about A and plus 1575 into 4.5. And from this we will get value of X bar is 2.63 meters. So center we have 3.3 meter, 3.3 meter and X bar. So we have CG same. So we have to coincide this CG with center of footing. And then we have this will be A, B. So this from center we have 2.63. Now we are interested to calculate value of A and value of B. Now how we will calculate this A and B? Now we know this distance 2.63. So total we have 3.3. Now this distance we have that is column width by 2, that is 0.35 by 2. And by using this 1, 2 and 3 dimensions, we will get value of A. So that value of A is calculated. A bar is 3.3 that is LF by 2 minus 2.63 that is X bar and minus 0.175 that is 0.35 by 2. We will get value of A bar 0.495 meters. Now we will see to B bar. Now this is important one. Now we have two choices. We can find this value and then we will subtract from 3.5. What will be this value? So we have this value as 4.5 minus 2.63 because we have distance center to center is 4.5. And we will get 4.5 minus 2.63 is 1.87. And then in the same way also we can find that I will write over here B bar that is equal to 3.3 minus 1.87 and distance that is from center to face. So we have 0.2 because 0.4 by 2 minus 0.2 and then we will get this value 3.3 minus 1.87 minus 0.2 comes 1.23 meters. And that we have calculated, you can see in this fashion. So same way 3.3 minus, this is 4.5 minus 2.63 plus 0.2. So if you will multiply by minus to both, so we have minus 1.87 minus 0.2 and that comes 1.23 meters. Now actual bearing pressure, we have column load upon area divided. So column load we have 1575. So this column load we have 1575 plus 1125 and that comes 2700 upon 2 into 6.6. So we have actual area 13.2, which will use 204.55 kilonewton per meter square. Now we will first design slab, and already we have seen we have to design it for transverse load. Now as we have slab, so let us we will consider width of slab as 1 meter, and as we are considering 1 meter, so we have to find spacing of reinforcement. If you will consider width of slab, then you have to find number of bars. And if you will assume width 1 meter, then you have to find spacing. So UDL of slab, as we are considering 1 meter, so we have actual bearing pressure we have calculated, that is, so now I will write WU equal to 204.55 into 1 meter, and that is equal to 204.55 kilonewton per meter. So multiplying by width. Then cantilever portion beyond face of column. Now see, now we are in transverse direction, and we have to consider minimum width of the column in that case. So we are likewise. So center we are going to be for the column load. So we have this value 0.35. And then what will be face beyond this? So we are with this distance. So we have this total value, we have 2 meters. So this is 2 meters. Now 2 minus 0.35 divided by 2, because we have on both side value as same. And then we will get 0.825 meters. So we have this value 0.825 meters. Then we will have bending moment at face of column, that is 204.55. So we know already, we have seen. Now this will act as a cantilever. So this will act as a cantilever, and load on this, that is 205.55. So we have this value. So value we have 204.55 kilonewton per meter. And then we have this cantilever is 0.825 meters. And then we have WL square by 2. And we have bending moment value, we got 69.61. So I will write over here 69.61 kilonewton meters. Now we can find depth for this. So simply we have formula RU into B. So RU we have 3.34, and B we have considered 1000, and we have depth 144.36, but we have to increase it. So we have provided the depth of slab, and that is equal to overall depth, that is 250 millimeters. And from this we will get 192 as effective depth. Now, as our slab is directly contact with soil, and therefore, as in footing, we are going to provide 60 mm cover. So here we are going to provide clear cover 60 mm, clear cover 60, and assume phi, that is diameter of bar, that is 16, because in footing we require 16. This is slab, but slab is for footing. So we have this will be 8. And from this we will get 68. And if we will go 250 minus 68, then we will have 217. Sorry, clear cover we have assumed 50, not 60. And then we have this value, that is 58. So we have this as 58. And then we will have this will be 9, and that 6, and that will be 9, 192 millimeter. So generally in footing we are taking effective cover 60. So here we are taking it as 50 clear cover, and till center we have 16 mm diameter bars. So it will be 5 by 2, and we will have this value 192 millimeters. Then we have reinforcement. This is simple 0.5 FCK upon Fy. And then we have substituted this value of mu. Now here we have to consider B as 1000. into 192 square. And we have this value AST required 912 mm square. AST minimum 0.12% BD. And then we have 300. So we have to provide AST 912 mm square. And then we have this value 16 mm diameter bars. So we have to find spacing. I already mentioned when you will take 1 meter as width, in that case, you have to find spacing of reinforcement. And from this, we will get value 1000 into small AST, as we have considered 16 mm diameter bars. So we have this will be small AST, 1000 small AST upon capital AST, and value we got 220.46. We have to provide less than this. So we have 16 mm diameter bar with 220 mm center to center. And then AST provided we got 913.19 millimeters square. Then we have next step, check depth for one-way shear about x-axis. So critical section at a distance dy from face of column. So we will find percentage reinforcement 100 AS upon BD, and that will be 100 into 913 upon 1000 into 192, and that is 0.48. So now we are going to calculate value of tau c. So we have considered these two values. So we have percentage 0.48. So these values were 0.25, 0.36, 0.5, 0.49. Now we have this table for K for slab, and for that we have to consider value of K. Actually, if we will go to just I will check that table. So we have that value of K over there. Okay, that we have to go through that table, and from that we will get value of K, and that for 250 we have this value as 1.1. So I just remember that table. Already we have seen that table in the class, and you have to use that, and then we have to consider that value of the K. So yes, 40.2 we have this value, and this is for shear, and therefore we have not used in our regular slabs. So we have value of table in clause number. So clause number 40.2, and then we have page number, that is 72. And there we have these values. And for this we will get value tau UC 0.48. So shear registered by concrete. So K tau UC BF into D. And from this we will get shear registered by concrete 101.38 kilonewtons. Now we have design shear. So 204.55 into we have 1 meter, that is width, and then we have 0.825 minus 0.192. So now how this comes? So we have in this way, column we have over here, and then we are considering in this fashion. So 1 meter width we have considered. This distance we have 0.825, and then minus 0.192, and then it will be somewhere here. We have considered, if you remember, in first footing, and this we have to consider. Now here again, instead of considering 6.6 meters, we are considering it as 1 meter, because width we have already considered 1 meter in slab, and therefore we have to go only 1 meter. So this is 1 meter width, and this will be this distance. And then VUD we will get from here 129, which is greater than 101.38. So we have to increase the reinforcement. So I have provided 6 mm diameter with 100 mm. Before this, we got it as, if we will go, then we have this 220. And I have reduced spacing, which will increase reinforcement So AST provided we got 2010.6. Then percentage we will get 1%. And then tau UC 0.64. And we have this value. If we will put all the values and calculate it, we have 135.17 kilonewton. And we have calculated actually this is 244.2. So 409.1 by 2. So 204.55. We have this value 204.55 into 1. So last we have taken same way. So 129.48 less than 135.17. And therefore, okay. So safe, that is against your one-way shear. Now we will go with transverse reinforcement, minimum reinforcement. So again, we have to provide spacing because we have taken 1 meter, and from this we will get 8 millimeter diameter bars with 160 mm center to center. Then we will go with design of longitudinal beam, and for that we have to draw SFD. Width of footing is 2 meter. So UDL along the length, that is 2 into 204.55, 409.1 kilonewton per meter. So now we have 1125 kilonewton, 1575.67, 1.43. So distance between the two is 4.5 meter, 409.1 kilonewton per meter. Now we will be with shear force. So now we have to first find shear force, that is under column A. So here we have to find value. So we will get it as 274.1. How we will get it? So we have 409.1 into 0.67. And from this we will get this value 274.1. Then we have 850.9. So now how we will get this value? So we have 274.1 minus 1125, because we have load of column A, this load 1125, it will go down, and therefore we will get this value. Then we have value that is under A, and we got this value 990.05. How we will get it? So we have minus 850.9 plus 409.1 into 4.5. And from this we will get this value 990.05. Then we have next value, that is 990.05 minus 1575. And we will get this value 585, and then we have 0. So we have this value that is of SFD. I have not mentioned unit over here, so I will write it as SFD in kilonewtons. Then we will go to the BMD. So we have this as SFD, and then we have point of zero shear force we have calculated. So how we have calculated point of zero force, shear force? So let us, we will consider this value as X, and then we will have 409.1 into X minus 1125, and that is equal to 0. And if we will calculate this value, then we have 2.749. So we have considered 2.74, because at this point we have to find maximum bending moment. So we have first, that is bending moment 91.8. To how we will get this? So we have 409.1 into x square by 2, because it is cantilever portion, 0.67 square by 2, and we will have this value 91.82. Now we will go at zero shear force, which will be maximum bending moment. Then how we will get this value then? So we have this value 409.1 into 2.75 square by 2 minus, due to load, column load 1125, 2.75 minus 0.67. So we have this 0.67, and from this we will get this value 793.1. Then we have 418.28. Now instead of coming from left, we can come from right, and we have this value 409.1 into 1.43 square by 2. And from this we will get it as 418.28. So this is value of BMD, sorry, this is diagram of BMD, and we will write BMD in kilonewton meter. Then we have next, that is depth from bending moment. Now we can find it very easily. I will not go in detail. Now important, we have considered this, that is 418.28. Now this is most important one. If we will draw the diagram, then we have this will be depth of slab. And then we have beam, that is, so I will just change the color. So beam will be from bottom only, and that will be till this. Means my slab is on bottom side. So we have this beam as inverted T-beam. Inverted T-beam. Now as we have single beam, so we have this as isolated T-beam. Isolated T-beam. T-beam. And then for this we have BF, and that is equal to L naught upon L naught by B plus 4 plus BW. And from this we will get width of flange. So here we do not have L naught by 6 or L naught by 12. So here we have to go, that is isolated T-beam, and this is inverted T-beam. Now I have column on this side. I have column on this side. So my diagram, if you will see, so we have bending moment diagram in this fashion. So we have likewise. Means in cantilever portion, my tension is on bottom, and in middle portion, my tension is in top. So in cantilever portion, slab goes in tension on both sides, and therefore that is no use. And the as no use, therefore in this portion, in cantilever portion, my beam will act as rectangular beam, and in middle portion between the column, it will act as isolated T-beam. Isolated T-beam. So depth, therefore we have considered value maximum 418.28 and not value which is at zero shear force. Zero shear force, because here my beam is T-beam and its strength is very large compared with your rectangular beam, and therefore I have designed it for 418.28 for depth. And then we have this value. So we have provided 850 because 750 I have already taken, but that is not satisfying the criteria of check depth for shear, and therefore I have increased it. And we have effective depth 900. Sorry, effective depth we have 850, and overall depth we have provided 900. So this is 900 mm, which is overall depth, and effective depth we have 850 millimeters. So now we have next, that is check depth for two-way shear. Now this is important one. So you can see this, I have shown the column. So dimensions I have shown. Now you can see we have this as depth of column, and we have D beyond the face of the column. So this is D by 2, because in this region we have beam, and therefore we have taken DB by 2. And in this region, so this region we have that is slab, and therefore we have taken ds by 2. So now depth available in this portion, we have that is depth of slab. So I will write here we have depth of slab, here we have depth of slab, and in this portion we have depth of beam. So how we will get them? So we have 2 times on this side and on this side, both sides. So we have ds plus ds by 2. So this is ds by 2. Depth available is this ds. So ds by 2, this total becomes ds, and depth available over there also ds. So we have, this will be ds into ds. Now in this region, this is width of beam B, and then depth available here is dB. So total we have that is B into dB. So this distance is B, and depth available is dB, and that is on both sides. So we have twice of this. So we will have clear perimeter along this. We have perimeter along this into depth. Now we have this along the length. So now we have this total D plus dB, because we have D and dB by 2, dB by 2 is dB. And depth available here is depth of slab. So we have D plus dB into ds into D, and we will have this will be area resisting shear. And we will substitute the values. And by substituting these values, we will get area resisting shear 1.194 meters square. Then shear critical at section. So we have same formula. I will not again explain in detail all these. You know shear at critical section. We have K into 0.25 root FCK. Shear strength at critical section, we will have 1.194 in 10 raised to 6 multiplied by shear at critical section, we have this value. Now here we have little bit change. So here we have column load minus W into area at critical section. Column load we have 1575 minus 204.55, 0.4 plus 1.192 and 0.4 plus 0.85. So we have values calculated accordingly. So if I will go likewise, so we have B that is 0.4, and one side we have that is depth of slab, and on one side we have that is depth of beam, and therefore 0.4 plus 0.85 and 0.4 plus 0.192. This is ds by 2, ds by 2 on both sides. This is dB by 2, dB by 2 on both sides. And then we will get this value 1423.56, which is less than 1075 kilonewton. So we have considered 1075 kilonewton. Sorry, this is not 10. So that when depth I have taken as 750, in that case I got this value. And now we have this value 1492.5 kilonewtons, and therefore safe. So now we have next, that is reinforcement. Now I will go a little bit fast. So we have this will be 25 into 400 into 650 square. So we have this as 400, and this is not 650 actually. We have this value that is 850. And then we got this value 1772.5 mm square. AST minimum is 384 mm square. 6 bars of 20 mm diameter along X direction. So we have calculated this. So now just check this. I have taken as 650 or 850, and accordingly you calculate the values. So we have this value at column B 1722.5, and we have to provide 6 bars of 20 mm diameter along X direction, that is along length. And then we have ASTA. So first I have put 418.28, and second we have that value something 92.5 or likewise. So that value we can calculate 409.1 into 0.67 square by 2. So that becomes 409.1 into 0.67 square by 2. So 91.8 to check it. And then we have to go for that moment is 325 less than 384. And we have to provide 4 bars of 12 mm diameter. Then we have between the column beam, I already mentioned this, it will act as T-beam, and then bending moment we have to find this L0. This is the distance between zero bending moment. And then we have calculated bending moment 0. I have considered left hand. We got two values, 1.78, another 4.72. So we have along the length 6.6 meter. One value we have over here, which is 0.78. And the second value we got, which is 4.72 meter. Both values we have from left hand. And then we have distance between zero bending moment is 4.72 minus 0.72. This will be 3.94, and this we will have value of L0. Then we will find value of BF, L0 upon L0 by B plus 4 plus 400. And we have 10559.97. Now we will consider, assume neutral axis lies in flange. Neutral axis lies in flange. And maximum value we are considering, so when lies in flange, we have mu is equal to 0.36 FCK XU into B in bracket D minus 0.42 XU. Now we are assuming that is XU is equal to BF. Sorry, DF, that is depth of slab. And then we are checking if mu is greater than mu, that is 709, then it is 793, then it is in flange. So we have to directly use value of AST, and for that one we have to use value of BF. So we have that B is mentioned over here 250, and by using this we are going to get, sorry, this is 0.42. So we will consider bottom one directly. So we have 0.36 FCK into BF into 10 BF into DF. This is depth of slab, depth of flange, into 850 minus 0.42 into DF, because we have considered XU equal to DF. And we got value 1776.77, which is greater than 793.1, and therefore neutral axis lies in flange. And then now we need not require to find value, because we have to find that is AST for 793.1, and we have calculated, we got 2259, minimum we have 1147.77, provide 20 mm diameter. So we have provide 16 mm diameter bars. So actually we have to provide it for beam, and as it is for beam, so we need not require to go for spacing. So we have used 20 mm diameter bars, and then we will get 2259.95 and divided by value we have, that is 314.16, and we will get 7.19. So provide 8 bars of 20 mm diameter. As we are designing beam, not slab, and our width that is equal to 400. Here we have BF, so we have to find number of bars over here. And then AST provided will be 2416.62 millimeter. Then shear reinforcement, we have to find shear force at point of contraflexion. And how we will find this? So you can have 850.9 value of shear force, or you can have 1125, and where we have that contraflexion, so into 0.78. You can go likewise also, so minus 409.1 into 0.78. So it comes 805.9. So that is at contraflexion, because at contraflexion means we have bending moment equal to 0, and we have calculated shear force over there. You can find from this, or you can find by using your SFD. So likewise, we have to find, I will not go in detail because you know all these shear resisted by concrete, then shear strength due to minimum shear, then VUR minimum we have, and likewise we have to find zone of shear reinforcement. This we have, that is at column A or near column A we can mention. And then we have second, that is at column B, we are in the same fashion, that is at B. And then we have to go for shear. Then actually we have to find last, that is side reinforcement, because whenever your depth goes more than 750, we have to provide side reinforcement, which is 0.1% of the area. So you can see any book and from that you can provide this side reinforcement. So now we will stop here only. Thank you.